Okay, here's another table. It occurred to me that one way to prove Goldbach is to show that as you systematically go through all of the sums of two primes, you will get all 2n. So rather than starting with 2n and going to the primes, you start with the primes and go to the 2n. And within that, I think you need a mechanism for recognizing primes. And here's a table. Another induction is kind of, maybe there's somewhere. The idea is you start with just 2, and you start with 0, and you have the rule that when you get, or I guess you could, well, you go to 1, at 1, the rule, let me correct myself, when you get a non-zero for all primes, then you add a prime. So at 1, that's a non-zero, I'll add 2. When I hit 3, I get a non-zero here, and I'll add a 3 there. So I have a rule for generating the primes. And I go down to 4. I deleted the composites. When I go to 4, I don't have that property. I have 0 as in it's 0 mod 2 and a mod 1 here. When I hit the next one, 5, I get 2 and 3 are non-zero, so that one generates a 5. And so forth. I keep the signature of the new prime. So this one, 1, 1, 2, generates a new prime 7. And eventually, when I start hitting later primes, I start to make an additional table. So that additional table is the sum of the columns that I'm generating as I go along and this row of primes that I'm generating as I go, and this row down here are primes that I'm growing. So that's a 10, 3 and 11 is 14, 16, 20, 22. My usual pattern is when I hit a prime, I generate the next composites, and I get their prime digits across here, appropriate for the number for the primes that are up here. So at this juncture, I would be at 13, and 13 is less than 14, so I would get all of these. So it starts to be a diagonal kind of situation where all the sums are over here, and at some point I'm exhausted all the sums, and I just keep a tally of the greatest sum of two primes over here. And maybe erase all those as impertinent, and then I hopefully would be able to say at some point I'm going to, that's the k case, the k plus 1 case, I will get the next k plus 1, 34 in this instance. So I keep on incrementing these. They all have zeros in their rows indicating their composite. 17 has non-zeros. Once again, I use that to generate column 17. And here's what's kind of interesting here. You can see why Goldbach might be right. That sure, these primes are getting sparse, 31, not till 37, 6, distance of 6. But they're also such that the primes you get are being added to smaller numbers. And so the numbers are not getting particularly large all the time. They're backtracking, like 19 goes back to small summons over here that go with it and keep the numbers down. So through 32, it's been covered. And is there an induction, with this idea that it'll work? Or is it just another cute display, another cute idea? Doesn't have, it reverses Goldbach from give me an N to give me, I'll give you 2 primes, to give me 2 primes, I'll give you an N. That will occur at maybe 19, or this or that, or for sure it'll occur by a certain point. Is it the case that for 16, which generates 32, I will definitely be there by the prime after 16, if you follow my drift? Is there some rule that can be established that gets rid of the induction and does a direct proof? I don't know if this is like a mind-boggling table. It has a dynamic quality to it, and it's giving lots of information. The what I call the prime digits for each number potentially as you're going down, as well as all of the 2n's that are being generated by a set of primes. So between all of that, does it drop out that for any 2n there are a row and column that will give you that 2n, question mark. So it's sort of like I've said in one paper that you find a simple one that you can't prove, and then you make it complicated, and you get that's too complicated to prove either, and then you see a simplification, and it ratchets up, all based on that initial table where you count from 0 to n and then n to 2n, and they line up. You do a sieve, and bingo, you're done. Somehow or another, crossing those out will not destroy them being aligned, being symmetric. Prove that, and we're done. All right, so I think we'll call that a wrap. Okay.